All right, good morning. My presentation this morning is going to be about also real-time hybrid simulation, but I'm going to talk about the special application to use real-time hybrid simulation combined with shake tables. So we're going to look at hybrid shake table testing, and I'm going to give you an overview on this concept, on why do we want to do it, motivation, and then go a little bit into the theory behind it. And then the main part of the presentation is really to look at 4 different applications where we have done this previously. So here's the outline. First, motivation and overview of the method, then a little bit about the theory and the implementation. Then the first application we're going to look at is the mid-level seismic isolation application that we ran here at the 1 degree of freedom shake table that you saw yesterday on the lab tour, I hope. Then we'll look into application with structural actuators, an application we did together with MTS at Tangi University. Then I'm going to talk a little bit about the tall building application to use shake tables, which we did at the pier shake table here, the 6 degree of freedom shake table, which is also the one that we will see a demo this afternoon. And then finally, I'm going to quickly touch a little bit on the commissioning test at LHPOST. That's the big outdoor shake table at UC San Diego, where we help them convert their shake table into a hybrid shake table. And then I'll give you the summary and conclusion. So, motivation and overview. Why do we want to do this? Well, many structures nowadays that we use exhibit significant rate of loading effects. And so that means that we need to do the testing near real time or preferably at real time. And large systems like tall buildings that we like to investigate, long span bridges, also soil foundation structure interaction problems are very difficult to test on shake tables because of their size and their weight. And so that's really where the concept of hybrid shake table testing is really a nice way to do this. So for example, if we have a shake table and we want to test this tall building here, and maybe the tall building has a tune mass damper on top of it, to do this in full size on a shake table becomes impossible, right? However, if we do this as a hybrid test or a hybrid shake table test, what we can do, we can put the whole tall building structure into the numerical model, and we only put the tune mass damper on our shake table. And then basically what we have to do is analyze the numerical tall building, figure out what the roof response is in real time, and feed that roof response into our shake table, which then shakes the tune mass damper. We measure the forces and feed them back into our numerical analysis. Another thing we can do if we have, for example, this mid-level isolation system, same concept. If we want to do this whole tall building with a mid-level isolation, on one shake table becomes very tricky to do this in full size, full scale. However, if we break it up, we might be able to actually fit the top portion of the structure that sits on the isolation onto the shake table, and then we numerically simulate the bottom portion. So that's kind of the concept. Further, we can also do the dynamic testing of these full-scale specimens then really without these limitations that we typically see on the size, the strength, and the weight of our specimens. And another thing is that with very little effort we can perform a range of parameter studies by just changing the bottom. If I go back to here, we can quickly, for example, for this structure here with the mid-level isolation, we can quickly do parameter studies by adjusting to the numerical model here and running over and over. Especially because the top structure with the isolation being on the shake table is non-destructive. So we can run again and again, looking at different parameters in the system and do parameter studies like this. So it's a very nice concept. Well, I guess the formulas are still not quite showing correctly. So these are just the double dots and single dots there, time derivatives. So if we do the hybrid shake table testing, basically, we would have a structure like this. We feed in the motion at the bottom, and we shake it. And as you can see, the gray parts here, the bottom part, that's the numerical part, and the blue parts on top, those are the experimental parts. And so in our equations of motion, we see we have a combination now that we have the gray parts, we have basically the inertia terms, we have the energy dissipation terms, but then on the resisting force terms, that really becomes a combination of the two, how it comes into our equations of motion. It's just one way of representing it. Another way you could show it is like Sean just showed in the previous presentation. But then if I show it like this, if everything, this resisting force term is all lumped together, then now, because this is a real-time system, now this resisting force term not only depends on our displacements, it's not just a function of displacements, but it's actually a function of velocities and accelerations as well. So these are the different parts. So then we replace this top structure with our experiment sitting on our shake table in the laboratory. Put this like this on the shake table. This is the peer shake table next door that you saw yesterday during the lab tour. And put this on there, and then we run this hybrid shake table test. Another nice thing is, like other hybrid simulations as well, even for the hybrid shake table test, we can actually have the dynamic loading cannot just be the seismic loading. This can also become wind loading. So it's a very nice concept that you could look at tall buildings and you do a wind tunnel test, and you figure out what the loading is from the wind tunnel test, put this on your numerical structure, and then have a tuned mass damper on top of your tall building and do kind of a wind application using this concept. You could also look at other loadings like blast impact, wave loading, and traffic loading doing this. So if we look at this concept a little further, for a tall building application, I'll also show a bridge application. So that's how we're going to do it. We're basically going to have our structure here on the left, where we have the analytical portion at the bottom, and we're feeding in the ground motion down here in terms of, and we're feeding this ground motion not just in terms of accelerations, but we're feeding it in terms of ground displacements, ground velocities, and ground accelerations, because it's going to give us a more accurate solution. And then we have our interface degrees of freedom at the top of our numerical structure here. And this can be multiple degrees of freedom. So if we do this on the peer shake table over here, 6 degrees of freedom, so we could have all 3 translational and the 3 rotational degrees of freedom at the interface here. And then we basically use OpenFresco, as in a regular hybrid simulation, and we feed these interface displacements through OpenFresco into our shake table in real time. And we shake the shake table with our top portion, the experimental part that sits on the isolators. We shake that. And we put load cells under it so that we can measure these interface forces. So that's one way to do this accurately, is actually putting load cells there. Another way would be to do an observer, and I'll go a little bit into that in one of the applications later. But preferably we want to put load cells there. We measure the forces and feed them back through OpenFresco in real time into our analytical model. So that's the tall building application. We can obviously also do this for bridges. So one way of doing this, if we had like a long span bridge and we wanted to test one portion of it, one segment of the bridge in real time on the shake table, that's what we could be doing. And basically again, we build this portion of the bridge deck with the isolators on a shake table. Maybe we even have one structural actuator in addition to that, and we shake everything, and we feed again through OpenFresco our interface degrees of freedom through OpenFresco over to the shake table and the structural dynamic actuator, and basically then measure forces at all these interfaces and feed them back through OpenFresco. So a little bit more about the theory and the implementation. And we have heard just a really nice talk by Sean about the differences when you have like this division of the masses and what works well and what doesn't work well. So this tall building application actually, which is also the demo that we'll show later, is actually one of the cases that works well, because we have a lot of mass in our numerical substructure. So when we look, so I'm also going to show some equations of motions, not too many. So for a slow, and I just want to really highlight the difference between doing a slow test, a rapid test, and then doing a real-time test, and then the hybrid shake table test. So in a slow test, we have the equations of motions as such, and similar to the way what Sean Gao just showed, we can divide this up into a part, and I'm using A and E subscript instead of N and E. So A for analytical portion or numerical portion, and E for the experimental portion. So that's how we split it up. In a slow test, we have all the the inertia parts and the energy dissipation parts, that's all numerical. But then for the resisting force parts, we have an analytical portion, which then typically depends on displacements and velocities, so that's a function of that. And then for our experimental portion, because we're assuming it's rate independent, we're doing it slowly, that resisting force term on the experimental part only depends on the displacements, okay? If we do this in a rapid test, and we look at what happens here in this resisting force term, well, actually we will start picking up some inertia part and some energy dissipation, right? We're not doing it in real time yet, we're doing it somewhere in between very slow and real time. But we're in the experimental part, because we're moving it a little faster. We're starting obviously to pick up some inertia because the specimen has some mass, it has some energy dissipation in there. So we're starting to pick that up. What we can do to make this correct, we can basically measure accelerations and velocities, and we can correct the forces that we measure from our load cells. We correct those by those measured accelerations and measured velocities by knowing what the mass and the damping is. We have to obviously, the damping might be a little tricky to know what that is, but we correct the measured part before we feed it back into our analysis, right? Before we put it. Now if we do this in real time, so we're doing it an actual wall clock time to be the same as our analysis time, we're doing it in real time. Again, we can split this up, but now we don't have to correct, because right now our resisting force term from our experiment is now dependent on not only displacements, but also velocities and accelerations, and we're capturing this correctly. All right? And so basically, if you look at this, we can then split this up, and this has the inertia in it there and the energy dissipation. So it's a combination of just the stiffness part and then the dynamic portions that go in. Now finally, if we do this as a smart shaking table test, which is what we're looking at here, this now is quite similar. Your resisting force term is quite similar to what we did for a real-time test. The one big difference is right there. So our displacements, velocities, and accelerations are not relative values anymore, but they're actually absolute values, and that's the T, or total values. So that's what we need to do. The ground needs to be part of it, right? Because when we shake, like if you think of the tall building application, and we want to know what the roof is doing at the interface degree of freedom, where our tune mass damper is, what we need to send to the shake table is not a relative to ground, but is actually an absolute to ground. And that's the difference there. Some other things that we need to consider when we do these types of tests is what we've been using is either we can use this in OpenSees, and sometimes we do it in OpenSees SP, it's a parallel version to make this go really fast, or we can do it directly in Simulink as a computational driver. Basically what Jean Gao showed. We can do this conversion, put everything into Simulink, and do it there, instead of having an interaction with an actual finite element software. So we can do both applications, and we've tried both of these when we do these real-time hybrid shake table tests. Then in terms of integration methods, it becomes sort of important that we use some integration method that is quick, that is real-time compatible, and that has some numerical damping in there, that we can kind of damp out those higher mode effects that Jean Gao showed, like those higher frequencies, because they start accumulating those errors much faster. As we've seen from his presentation, the negative damping is much more pronounced on those higher modes, and so we can damp them back down by using some numerical integration method that has energy dissipation built into it. And so one of the really good methods is this alpha operator splitting generalized method, and then we also have been using more recently this KR alpha method that I mentioned yesterday, developed at Lehigh University. And so these basically have this adjustable parameter to put in numerical energy dissipation into the system. And both of these integrators require no iterations, so they're very fast in solving. As I've already said, at the bottom of the structure, typically we don't want to just feed in accelerations, but we want to actually feed in ground displacements, ground velocities, and ground accelerations. And in OpenSees, this is really easy to do using the multi-support excitation pattern. Even if you only have one input in terms of you're not doing different inputs at different supports, so using the same input at all your supports, you can still use this multi-support excitation pattern, and it actually makes it so that the whole system of equation in OpenSees is then solved in the absolute coordinate system, not the relative coordinate system, and that's what we need. Finally, one important thing about gravity loads. The gravity loads in your test specimen, when you put this on the shake table, obviously it has your mass and everything there. So the gravity loads, they always exist. They're there in your experimental portion. And you want to apply these gravity loads also to your numerical part. So if you have a tall building and you have a heavy tune mass damper on top, that weight should also go into your numerical analysis. How do you do this? So typically you then do it differently than when you do in a normal analysis. You basically put your gravity loads into the numerical portion before you connect with your shake table. Because otherwise, when you do the static analysis, if you put this before, basically if you put your gravity load, you first connect to your shake table and then you put your gravity load and then you need to do your static analysis, you're going to have trouble during your static analysis. So the way to get around on this is basically you put your gravity loads onto your numerical model before you connect, then you connect with your shake table, but that means your numerical model will have already settled a little bit. And so your first, in vertical direction on your shake table, you will already have a command there. So what you need to do, you need to control your shake table relative from that point. Otherwise, the shake table will in your first step just go down because your numerical model has already shortened. So you basically control the relative. How do we connect everything together? So we are using, for these tests, we're using the MTS469D, that's the shake table digital controller system. And so that's how we connect. So on the top we have our OpenSees finite element model. And then in the middle, as yesterday for the slow stuff that we looked at, we have OpenFresco, the middleware, right there. And we're doing this as you can see on the left here, we're doing this as a local test. Obviously, because we got to do this as fast as possible. So we want to have minimum delays. So local test. And then from OpenFresco, we got to talk to our XPC target, or newly it's called Simulink real time, where we run our predictor corrector model. And so we talk through that through ScramNet GT. So yesterday what we looked at in the 484 lab was actually using ScramNet. What we will see today on the shake table is using ScramNet GT. It's just a newer version of ScramNet. ScramNet, the old version, has actually been discontinued. So ScramNet GT is being used again, like yesterday, to connect all these real-time machines together. And so we have our XPC target here that runs the predictor corrector. And then at the bottom now, we have the MTS469D, the shake table controller. And if we have additional structural actuators, like dynamic actuators, which is one of the applications I will show, we also have maybe the MTS flex test controller that also sits on this ScramNet ring. And so we can talk to both of them simultaneously. It's all synchronized through ScramNet, and that's how we finally talk to the specimen in the laboratory. Few words about stability and accuracy. We've seen in the previous talk, very, very important that we, in these real-time hybrid simulations, delays. That becomes very, very important. And so what we need to do is we need to compensate for those delays if they're existing there. Otherwise, as we've seen in Sean's talk, any small delay is really going to make things go unstable. What we have found is very, very effective in doing this is this adaptive time series, ATS, delay compensator that was developed by Professor Che at Old Dominion. And he did this during his PhD at Lehigh University when he was working with Jim Rickles. So they came up with this ATS compensator, which is based on some least squares approximation. And it's sort of, we've been treating it a little bit as a black box, like it's just been a magic box, I call it. It has been working really, really well for us. And on the shake table here, I think we start off with about 30 milliseconds of delay when we do these tests. And from Sean Gau's talk, 30 milliseconds, it's not possible, it's not going to work, right? And so using the ATS compensator, on average, we bring it down to 0. It works really, really well. We have slightly modified the ATS as it was implemented by Professor Chow. Originally, we made some minor modifications to improve it a little bit. Then other things we can do is use stabilization and do some loop shaping, kind of like what Shangao was showing in the previous talk. And what is also important is sensor noise reduction by filtering feedbacks. So if our feedbacks have a lot of noise on them, we want to try to get rid of that so we're not feeding it back. So this is the 3-loop architecture that we've seen yesterday. So we're using this as well for the shake table test. So if we do, this is basically doing a soft real-time shake table test. But really we're actually achieving hard real-time as long as we don't have any delays in our predictor corrector. So the same way as we do it for the slow test, we can do this for the real-time shake table test. We have the outer loop, which is our integration loop, which runs at 1 time scale. And then we have the very inner loop, the servo control loop, that runs at a much faster time scale. Actually, for the shake table here, it's running at 2048 Hertz, so twice as fast as what we've seen yesterday. Not 1 millisecond, but half a millisecond. So that's the rate in here. And to bridge these 2 time scales, again in the middle, we are using the predictor corrector algorithm that predicts, while we're waiting for this guy to come up with the next target, we're predicting out, and as soon as the target comes in, we're correcting towards that target. And as long as we never go into this slowdown state in the predictor corrector that we talked about yesterday, we actually achieve hard real-time, not soft real-time. And the ATS compensator is basically implemented directly here, in the real-time system on this XPC target where the predictor corrector is sitting. Then over here for the controller, we are actually using the 3-variable control by MTS. But the other advanced controllers and force balancing schemes can be used. But we like the TVC. Then in here we can also put the filtering that I mentioned for the noise reduction. So these filtering algorithms can also be directly implemented into the XPC target machine. Another nice thing that we can do with these tests is that we can do test rehearsals before we do the actual test. And to do that, we can use the FE adapter element approach that Sean Yu showed yesterday. And we can really have, basically in parallel to our real specimen, we can create in parallel the numerical specimen. So they're both existing there. And then we basically have a dial in the middle, and we can start off and say our feedback force is now first coming 100% from our numerical analysis. We're still shaking the table, but the forces, instead of measuring the forces at the bottom from the load cells, we're using our analytical model to feed it back. And so we're doing a safe test. And then when we feel confident, we start turning this dial. And we maybe put 50% of the feedback from the real thing, 50% from the analysis, and then finally we go all the way to 100% feedback from the specimen. Other things we need to look at is safety precautions. On the analysis side, we got to make sure we're setting limits correctly. We can put saturation and displacement limit commands there. So for the rate and the displacement, we can set limits on actuator forces, so that's important. And we can do this both at the analysis side and at the controller side, so we can have double the safety there. So now let's go into these applications. So the first application I like to show is the mid-level seismic isolation application. So what's a mid-level seismic application? Maybe a few words about that. It's really there to provide architectural flexibility in buildings. It can be a transition between different structural systems, so you can have one type of structural system at the bottom, another type of structural system on top, and then you put an isolation in between there. And it has been done in several applications out there. So this is China Basin that's out in San Francisco, and this was an existing building that existed up to there, and they wanted to, much later, put extra stories on top of that existing building. So what they decided to do to make this work, they put an isolation system right in there before they put the new parts on top. So we can basically, you kind of create like almost like a tuned or untuned mass temper really. It's like an untuned mass temper that you put on top of your existing building. And by doing that, you can actually make sure that the seismic demands on your existing part are staying quite low, and also the seismic demands obviously on the part that is above stay low. So this is, yeah, like I already said, provides some architectural flexibility. And another good application is sometimes you can, when you have this isolation level raised, not at the bottom, then you don't have to deal with like other things like mode clearances and all these things. So that might be an advantage as well. So we did this. We basically built this special purpose, and I think you've seen it yesterday in the laboratory during the lab tour, this 1 degree of freedom shake table that we have at the lab in 484. So we have that. The specimen that we put on top of it was basically this 2-story isolated structure, and this is like this reconfigurable structure that we have here at the Pier lab that has like all these clevisons with coupons that we've seen in the small component application yesterday. We actually have a lot of those, and we can build up whole structures that then can have like plastic hinges at all these locations. But for this application, we just used it to build up a frame, and then we have the seismic isolation down here. So that's what was on the shake table. The seismic isolation system that we used for this was this triple friction pendulum system. Was at the 3rd scale, and you can see the effective period of this system is 1.4 seconds. It's actually the same isolation system that we will be using during the demo this afternoon. In terms of the analytical substructure that sits below our isolated experimental test specimen, we had 2 models. We had a model A, which was a 1-story substructure, and then we had a model B, which was a 3-story substructure. And we basically looked at different frequencies or different periods on these different models. So that's, like I said, we could do these parameter studies by quickly changing the properties of our numerical part of the structure and adjusting the parameters there. In terms of response, we then ran all these different models. So you see model A, we ran the substructure with different frequencies or periods. We ran a substructure that had a 1 second period, half, quarter, and then 1/8. And then for the model B, the 3-story substructure, we did similar thing. We ran it at 1, half a second, and a quarter. Didn't do the 1/8. And then we can do these comparisons and see how it's doing. One thing it's hard to see, especially probably in the back here. So if we look in the frequency domain and we look at the error command, which is this command in time domain, and we plot this again as an FFT in the frequency domain, you can see that exactly what Zhang Gao was showing too in his presentation. For these multi-degree of freedom systems, this one is the 3 degree of freedom substructure. This is the 1 degree of freedom substructure. So for this multi-degree of freedom system, you can see we're starting having these higher mode errors there that really start feeding into our response, which were not present over here, right? So you didn't see those there. Now they're appearing here. So that's because of errors. And so we further investigated this a little bit. We also plotted some more FFTs on accelerations at the different locations in our structure. So at the top of the substructure, at the isolation level, then at the superstructure, and at the roof. And we again started comparing. And you can see again in model B, out here, like 14 to 17 hertz, we have these modes that start really feeding in, which were almost not present over here, right? And these really started having problems. So if you actually look then at mode shapes, and we did this to really investigate what was going on, and because we have a triple friction pendulum isolator under the structure, this can respond either in its initial stiffness, the isolator, or the isolator can respond in post-yield stiffness, right, once the isolator starts moving. And so you can plot mode shapes assuming the initial stiffness or the post-yield stiffness. And if you look at this initial stiffness mode shapes for the whole structure, you see this mode 5 and 6 are at 14 and 17 hertz. And so these modes, really 5 and 6, were really being excited by experimental errors that we were making, because we had a little bit of delay in the system. But we didn't have ATS at this time when we were doing this, so we had some delays left there. And so that's really what was happening. Let's see if the movie plays here. Yeah, okay. So that was one of the tests. It's a little distorted because we had a fisheye camera to get it all. The space is really tight in the laboratory, so we had to put a fisheye camera very close to the specimen to really capture it. And unfortunately, you can't actually see that the isolators. They're like down there, right?
Right, yes.
So yeah, right here. So it's a little hard to see. While we were doing this, one more exciting thing actually, for those of you that know, in San Francisco there's the California Academy of Sciences. So they heard about this testing happening, and right at this time they were really interested in creating an exhibit for earthquakes, about seismology and earthquakes. So they decided to come out and film our testing while this was happening. So that was pretty cool. And then they had a movie about it at the Academy of Sciences back then, and yeah, they were just showing while we were doing the testing. So that was pretty neat. Okay, so application 2 I like to show is the testing that we did together with MTS at Tangi University. So this is an overview of the new lab at Tangi University. So this is this shake table array that they have. So they have these 2 trenches, and they have 4 shake tables that they can reconfigure the locations of those 4 tables. So right now you can see 2 of them are here, 1 is right there, and then the one we are using for our testing is right down here. So we have this specimen there. But by doing this reconfiguring, they can really test really long things like bridges. They can even do curved bridges by using the trenches in both of the trenches. So it's very flexible. Yeah, like I said in the title here. So all of these 4 tables are 2 degree of freedom shake tables. So they can move in both horizontal directions. Here's the overview of what we were testing. So this was our specimen. We were doing a bridge application. And so what we tried to do, it was very novel, and I think was the first time that anybody has done it on this full scale, that we were basically connecting or testing something that is a shake table in real time combined with a dynamic actuator in real time. So, and here's the development of the model. So we started off with a bridge deck that is seismically isolated. So there's isolators under it. Here's the bridge deck with the mass on top. And it had also the foundation and some soil. So that was all modeled. And so we basically had to make this very simplified model of this. It's I guess, a different way of model reduction technique than what we've seen from Shanghai. So what we did is we simplified this model basically into what I have over here. So we have like at the bottom an element representing our soil, and then an experimental element representing our bridge. So it's very simple thing. And it has then obviously the weight of the bridge deck on top of it. Right here, the remaining numerical mass. So some of the mass is actually on here, as you can see by these lead weights that are sitting on top of the bridge deck. And so the rest of the mass that is missing is the numerical model. So then we did what? So we ran a test like that first, where we just had this without a structural actuator, and then we ran a second test where we basically removed all these weights, and basically to simulate those weights we then have the structural actuator. So basically the mass that is now not sitting on top of the bridge deck is basically experimentally generated by this actuator. Okay. Another thing, I've already mentioned it once before, that we had to do for this, unfortunately we didn't have load cells. Ideally you would want to do load cells on the shake table to measure forces at your interface degrees of freedom. Unfortunately we didn't have this at Tangi University, so what we had to do instead was using an observer. And meaning an observer, what we're basically doing is, for the MTS shake table with the 469D controller, you can directly get the table degrees of freedom, right? So that's the DOF control that Sean Yu has been talking about yesterday. So we can directly get the table degrees of freedom. So at the table surface, we know what the forces are, and we can get the accelerations. So what we do is we basically get the force at the table degree of freedom, and also use the accelerations, and we assume, or we try to estimate as accurately as possible the weight of the table, and then we can take accelerations times the weight of the table, subtract that from our forces at the table degree of freedom, and that should then be the measured force at the base or at the interface degree of freedom. Okay, so that's the observer that we're doing. And so here's a movie of the test where we did this with the shake table and the actuator. Right, now we go.
One more clip.
Oh, that's unfortunate. That would have been exciting. Yeah, sorry. Somehow that movie is not playing. Okay, well, continue on. And then we can, afterwards, we can look at some displacement comparisons. We can look, we can assess the accuracy of these tests. And again, we did that assessment in terms of FFT, looking at tracking errors. We're looking at tracking indicators by Professor Merkan. We have normalized root mean square error histories that we're looking at, and we can do comparisons with our purely numerical simulation models. And so here's the response at the soil level. It's probably hard to see the green line, and then the bridge simulated is in red, and the bridge tested is in blue. So we can see that our actual, we get pretty good match there. In terms of forces, we can also look what the table is doing in terms of forces and what the actuator is doing in terms of forces. And so here, again, sorry for the color selection here, it's a little hard to see. Yeah, we can compare this from the simulation again, meaning the pink and the red colors versus the actual test, the light blue versus the dark blue colors. And then we can go into the frequency domain and look at the assessment there, and we can see what different modes we're picking up. Again, basically figuring out how well we're doing. Then very important, obviously, like I said, in real-time hybrid simulation, delays. It's really so much is about delays. And so after testing, we want to see how well are we doing in terms of delays. And so we're basically plotting here the displacement histories, and we're doing it in terms of the target versus the measured. So blue is target, red is measured. And as you can see, and then I do an assessment to figure out what is the mean delay over the whole response, basically over the whole like 40 seconds. What's the mean delay? And the mean delay actually is at 0. So no delay on average. And so the ATS, because we were using ATS compensator on this, is doing exceptionally well and is getting rid of the whole delay. Again, for this test at Tongji University, I think we started off with 40 milliseconds, if I remember correctly. 30 milliseconds. And this brought it down to 0. Okay, then application C, searching will be the tall building application that we did here on the pier shake table. So we have the 6 degree of freedom shake table that we'll see the demo later this afternoon. And we put on top of it basically a tune mass damper, like that tall building application that I was showing at the very beginning of my presentation. The pier shake table is 20 by 20 feet, so 6 by 6 meters. It's, I think, still the largest 6 degree of freedom shake table in the US. It can test structures up to 100,000 pounds, and we can achieve up to 1.5 Gs in terms of accelerations. Displacement-wise, it's on the smaller side because it's an old table. It has both horizontal directions are plus minus 5 inches, and the vertical direction is plus minus 2 inches. Velocities that we can achieve are about 40 inches per second. We were using the same bearings again because we had them. So the triple friction pendulum bearings, again we can see the modes here. So this is if it responds in stage 1, just the inner slider going, we're at about 0.67 seconds. If it starts moving on the outer, just on one side, we're at 1.4 seconds, and if it moves on both outer ones, we're at 1.87 seconds. So that's the period. So that's good to remember for the demo later. In terms of analytical substructures, what we did, we basically created different models. So I have what we call the models without rotational degrees of freedom. So I have a model B and a model C. So starting off maybe with the model B, I had a very simple structure. So I just have basically a 1 degree of freedom substructure. And again, this represents now the whole tall building, okay? And so that's basically what Shangao was saying. So in our numerical simulation, we actually, our mass or weight is actually really big compared to what the tuned mass damper is doing on top of it. So it helps us doing these tests. The other thing that helps us is to have the seismic isolation. It's very, very forgiving in terms of testing, because the modes that we're seeing on the actual test specimen are very well behaved. They're like low frequency. And so that's what we did. So for each direction we had 1 degree of freedom. Okay, so it becomes a 3 degree of freedom system because we're not doing rotation. So we're doing 2 horizontal and 1 vertical degree of freedom. So that's why it's 3. Then we also did one where we represented the tall building in terms of more modes, because we wanted to see what happens when we include higher frequency modes. And so we created a 5 degree of freedom system in each direction, so it ends up again with 15 degrees of freedom because of the 3 directions. And so then we ran this. And again, we can adjust, as before, we can adjust the frequencies of the substructure, because it's numerically, very easily by just changing the numerical properties of the substructure. And so we ran this at like 1 hertz, half a hertz, a quarter, and then all the way to 1/8. Then finally we wanted to do something with many degrees of freedom, so we took one of the students here had a model because he was looking at base isolation of tall buildings. He had a tall building model, a shear representation of this tall building. So this was a 30 degree of freedom model, so we also ran that. So hopefully this movie will play. Let's see. So if this plays, this should be one of the tests with rotational degrees of freedom. So the table is now not just translating in the 3 directions, but it also has the pitch and the roll. No yaw, but the pitch and the roll. And the reason is because we also had some models, I didn't show it, we also had models that are not shear representations of building, but actual flexural representations of building. So especially on a tall building, obviously at the very roof of the building, you're going to see rotations. And so if you have a tuned mass damper on top of the roof, and you have rotations there, you really want to see what happens to the tuned mass damper, including those rotations. So that's when it becomes important. And so that's why when we run this test, you might see it, yeah, that the table is also has the roll and the pitch. Once we were done with this, again, we wanted to assess how well we were doing these tests. So first thing we looked at were delays. So in terms of delays, again, on an average sense, over the history of 45 seconds, again, using ATS compensator, brought it down to 0. We started off somewhere between, on our table here, somewhere between 30 to 35 milliseconds delay, if there's no compensation. Same thing for the 2nd degree of freedom. So the first one was longitudinal. This is lateral degree of freedom translation, also at 0. And then the vertical, it's not perfect. So vertical performance on this table is a lot harder to achieve. So there we had a little bit of delay left, 2 milliseconds in the system, but it didn't go unstable. Then we plotted some tracking indicators and also the normalized root mean square errors. So we can do those and see what each degree of freedom does. And like yesterday, what we've seen, so the tracking indicators, it's actually a very small, this is in millimeters square, so it's a very small value. So you can see degree of freedom 1, meaning longitudinal table degree of freedom, is doing very well. Has a tiny bit actually of lead. and then degree of freedom 2 has a little more, so that's actually helping us. It's not like we learned yesterday, it actually introduces a little bit of energy dissipation into the systems, but then the vertical degree of freedom we had a little bit of lag, so there we're actually putting extra energy into the system, so negative damping. So that one can hurt us, but it stayed stable. Then if we look at this in terms of normalized root mean square errors, we can assess that for the different models that we looked at, different degrees of freedom, and these are in percent. And so you can see we're staying like way well below 1% for any of this. The only one, like here, is maybe that test D where we had the pitch, the roll and the pitch and roll. And we had a little bit above 1%, but still very good. One thing that we were facing sort of problem was there is a lot of, we're measuring forces during these tests from load cells. We're not doing an observer. But even with our load cells, we still have a lot of noise on those. It's a lot better than doing an observer, but it's still, the noise is still there. And so what we started doing is like we started filtering. So we had to create some notch filters to take out some of that artificial noise that was there. And so we were able to improve this. But that clearly needs more work to figure out exactly what we want to do there. And then finally we can look at the response of the building itself. We can look at what happens at the ground level, at the roof level with TMD, and at the roof level when we don't have a TMD. Okay? And you can now see that actually when we put this tuned mass damper at the roof level, yeah, it's I guess the line color is not the best again. Maybe down here it's easier to see. We can actually look, if we look at a response spectrum at these different levels, we can see that the green line is actually, with the TMD, is doing better than the red line without the TMD. So we do get an improvement from putting that tuned mass damper on top of the whole building. So finally, the last application I want to touch on is this commissioning test that we worked together actually with UC San Diego, the LHPOST, their large outdoor shake table that they have there. This is a 1 degree of freedom shake table. It's the largest shake table in terms of dimension in the US, but it only has 1 degree of freedom. And as you can see, it's outdoors. So it has advantages of being outdoors, being able to do very tall specimens, but it also has obviously disadvantages because you have you have the weather to deal with and the whole environment to deal with because you're not indoors. But they wanted part of the, like UC San Diego is now one of the NRMSE experimental sites. For those of you that know, and they wanted to convert, as part of NRMSE, they wanted to convert this shake table into a hybrid shake table. And here at Berkeley we have the NRMSE Simulation Center, and so we basically collaborated with them to go down there, and because we had already the expertise here from Berkeley, because we've been doing it many times, to go down there and collaborate with the researchers at UCSD to convert their table into a hybrid table. The approach that we took was similar. We actually shipped our specimen, meaning the isolators, our load cells from Berkeley, because they didn't have load cells. The steel plates, all that was shipped from here, because we want to try to repeat the exact same 1D test that we did here, so we can compare results. And so we shipped that down. The blocks were a little hard to ship, so they cast their own concrete blocks, but the same weight as what we have here. And this will be exactly what we're going to see in the demo too this afternoon. And so we repeated these experiments, so the setup looked the same. So we had OpenSees finite element model on top, we had OpenFresco middleware. There they don't have ScramNet GT, they have the older version, they have ScramNet on their controller, so we were using that. And then we had a real-time predictor corrector in the middle. And then finally down here again we have the MTS 469D controller. One thing we had to do differently is that our MTS 469D controller, we actually got this from MTS on purpose with extra conditioners on it, so that we can actually feed all our load cell channels, all these measurements, through the controller. because we want to have everything synchronized perfectly. So we didn't want to use a separate DAC system, because then we would have to start dealing with synchronization issues between the control system and the data acquisition system to get those load cell measurements back into the analysis model. So we have extra conditioners on our system, and so we can easily feed, we have 40 channels available, so we can easily feed all these load cell channels through the controller to get the forces back. Now, unfortunately, UC San Diego doesn't have that, so they didn't have these extra conditioners. But what they did have is an MTS STS controller, which is the same that we were using yesterday for the demos. So they have that, and all of those sitting on the ScramNet ring. And so we were using basically the actuator channels on the MTS STS, the force channels on those actuators, to get the load cell measurements. And so that's how we were able to basically send out the displacement commands through one controller, the 469D, but to get the force measurements back through the other controller, the STS. So this is the same detail I just showed. So basically, that's their setup here in the lab. You see the 469D controller box here, and then you see the STS next to it. And everything is connected with the ScramNet Plus, the older version of the ScramNet. Thank you. This is the control room layout. So we have all the different, there's a lot of computers obviously that you have. So over here we have the person controlling the 469D, that's Darren, and then we have some visualization software in the middle here. We have the data acquisition system, because we did take some other measurements in terms of accelerations and displacements of the specimen and so on. So this was independent data acquisition system. Then we have the STS right there, that's Professor Mosqueda. And so that was used for the force feedback, and then we have the XPC, the real-time and also the XPC host, XPC target interface here where I'm sitting. Then we have the comparison of the results. So we ran this actually twice. We ran this with OpenSees OpenFresco approach, but then we also ran this with a pure Simulink approach, where we have the whole numerical analysis, everything implemented in Simulink. And the OpenSees OpenFresco approach is the one with the predictor corrector. And so we ran this exact same thing twice, and we can see we get very, very similar response in terms of hysteretic behavior on the isolators. We can also compare different reference signals of the shake table, and we can basically, by doing this, we can see that what the ATS, we were using ATS again on this whole thing, what the ATS is doing to predict something that is a little shifted and has a little higher peaks, to basically compensate for delays and or undershoot. So summary and conclusions. I basically showed you that we have this ability to drive very large shake tables, and we've done it many times on different tables through finite element models, and we can do this in real time, as we have to do that for a shake table, hybrid shake table test. Shake table platforms can also represent floors and roofs of buildings, and the top of the motion of bridge columns can also be done. Or we can do at the ground surface, where we have a soil domain numerically modeled, and the shake table represents the ground surface on top of that numerically modeled soil domain. We have the ability to do parameter studies through this, and also the ATS delay compensator, one more time, it has worked super well for us, and we're very happy with that. So these types of tests we can use whenever dynamics of the test specimen significantly affect the response of the supporting structure or the soil, and therefore alters the required input to the shake table. So if the specimen dynamics doesn't affect the response of the numerical part, then we don't have to do it. But if there's that interaction happening, that's when we want to do the hybrid shake table test. What I feel, or what we feel that still is needed, is like more investigation into the sensor noises and how they feed back into the analysis and how they affect the analysis, and how can we get rid of those or compensate or at least reduce them to a certain degree. All right. Thank you very much.